Okay, so taking this right-hand rule forward, looking at an example, something called a solenoid. You'll find them in vehicles, in starters, and you'll also find them in the doors of your car, and they're the electric, the automatic locks. So basically, I'm going to take that coil, so I'm just going to draw a small version up here. So again, taking that coil, making it look something like that. All right, what I'm going to do is I'm going to take a saw, I'm going to cut it right here. Okay, so we're going to cut off the tops of these coils, and then I'm going to look down on them. Okay, so look down. So what do you see? If you're to cut off those wires, you're going to see the following. I'm going to see, and I'm going to start at, let's call that point 1 here. I'm going to see this wire has been cut off, and then it looped forward. So that means I would have, just move mine up a little bit here. So I'm going to look at that first wire there. It's been cut. And then point 2 is right there. So I'm going to have a wire that goes up and over. Underneath comes up here. And what happens is it just looks like a series of circles. I'm trying to make the same size close to, since the wire is probably going to be consistent. There we go. That's probably lots right there. Okay. So there's the coil, exaggerated. So we're looking down on it, and all we see are these cut wires. Okay. The textbook has a convention, so I use it all the time, and I put it on the text or the test, so you don't have to memorize this or put it on the sheet. But if it's an X, it's going into page. If it's a dot, this is the convention you'll have with the homework, it's out of page. So what does that mean? Well, at point 1, and I guess I better pick a direction here. So let's use what was on the previous example. That was negative, and that's positive. Okay? So with conventional flow, at point 1, if this is the negative terminal, okay, remember that conventional flow is positive and negative, so it's going to be going down at this point, trying to get out. So that means it's going into the page of that wire because it's escaping, which means that all of the wires that loop around this way are going to be going into the page. Okay? Which means that the ones on this side are how the electrons are getting to the top of the page. So they're coming out of page. So it just represents that the electrons are coming. You wouldn't want to draw this, but they go into the page here, and it loops down. So this is the wire, comes up and over top. So what we've done is I've cut, and we're not drawing the wire anymore. So there's the coil, okay? But we've got eliminated the coil, so get rid of those green lines. Okay? So what we want to do is look at what is happening inside using that right-hand rule number 2. So what do we know first of all? Using right-hand rule number 2, your fingertips curl in the direction of current. So fingertips always go on your X's or into pages. All right? So your fingertips always go on the into page ones. All right? So in order for me to put my fingertips on those 4 locations, my thumb is pointing to the right, which means that this end will be north and this end will be south. So inside a coil or a solenoid, the magnetic field is uniform and parallel. So I'm going to draw 4 lines, 4 bars. Okay. And then it acts like a bar magnet. So these field lines actually will loop around and connect again. Okay, so it acts the exact same as a bar magnet. So we really have created our own bar magnet with no magnetic materials. Okay, so we just done it with electricity. So there is our solenoid. Now the one extension to this is that those individual copper wires can be considered individual straight conductors, which means each of them will have a magnetic field. So then we use right-hand rule number 1. Okay, so right-hand rule number 2. So right-hand number 2 gives us these field lines. Right-hand rule number 1 is going to give me the ones in here. So what's a solid dot mean? Solid dot means the current's coming out of the page. So that means my thumb is pointing out of the computer screen at you, which means my fingers are curled around this wire in this direction. So what happens is we have two different types of magnetic fields interacting in a solenoid. All right. For the ones above, the X's are going into the page, so now my thumb is going into your computer screen, which forces my fingers to curl this direction. So what happens with the solenoid then, you now have two magnetic fields interacting. All right. So there we go. You don't want to add any more. I'm going to just draw something in to emphasize it here. Two magnetic fields. This magnetic field in the middle is pushing the whatever it is, the piece of metal to the left, let's say. These ones here are also pushing it to the left. This one here is also pushing it to the left. So those circular magnetic fields are also helping or strengthening that magnetic field within in the solenoid. Okay. So again, if you need an explanation, I think a 3D model I can help you with and show you in class what it looks like. So what are some of the factors that determine the strength of an electromagnet? Current in the coil. So if I increase my current, so current again is I, if I increase current, then the strength, which we're going to call force, so magnetic force, will also increase. So if you can put more juice into the system, you will get a stronger magnet. Number of turns in the coil. So number of turns, I believe it's capital N, and we're going to use that next year. If I increase the number of turns, then my magnetic force will also increase. So the more coils, the more strength. Size of the coil, and I think it's small r. So if we increase the size of the coil, okay, so r is kind of like the radius because we're looking at a coil or a spiral pattern. If I make the hole in the middle larger, we actually reduce the magnetic force. And that again is because if we go back, those four lines that I have represented in there, so these four magnetic field lines that are represented in there, if you give them more space, they can spread out. But if we put them closer together, those four lines get tighter and tighter, which means that you're increasing the magnetic strength. And then type of material, and let's call it type of material. I'm just going to represent it with a B. So the stronger the magnetic permeability, and you do not have to regurgitate this on a test, this is more grade 12. If it has a better magnetic permeability, you are making a stronger magnet. So if you are using iron and copper, you are going to create a better electromagnet than using some of the other materials that are available. Okay? So those are things that we can talk about in general, all right? Something that I'd ask in a true-false, nothing that you're going to have to regurgitate or explain. All right, so that's it. That finishes the lesson. What you're working with in the homework is diagrams that relate to the first two right-hand rules. Again, if you need some help with it visually or spatially, let me know, and we can create a sort of a 3D model so you can get a feel for what's going on. All right, good luck with the homework.